Hello, I'm here to take you through my final project for wireless communication. My name is Zeke-Travels, and the title of the project is the Performance Analysis of Smart Antenna Techniques in Wireless Communication. The need for increasing capacity has come of great interest, and the main way of increasing capacity has been arrived from reducing interference. So many kind of techniques have been introduced. We started for omnidirectional antennas, where you see this year an antenna actually serving the whole area. But it was realized that you have the interference of about 6 from co-channel interferences. Where to try to decrease this, the sectorized antenna was introduced using a three antenna, with 120-degree separation. We realized that the co-channel interference actually reduced too, and this improves capacity. However, we still realize that capacity can still be improved through some other techniques, hence the introduction of the smart antenna techniques. The smart antenna is an array of antenna elements that's connected to a signal digital processor to enhance capacity through diversity combination and interference suppression. It's used in so many areas, including the cellular and wireless networks, the radar and satellite systems, to name a few. The smart antenna technique provides higher capacity, higher coverage, higher bit rate, and mobility as well, hence its usage. There are two main types of smart antennas that are analyzed for my project, the switch beam and the adaptive array. In the switch beam technique, it forms a number of equal lobes around the cell, such that if a user is within a lobe, that lobe serves as its main antenna and processes its information. With the adaptive array, however, it follows the direction of arrival of the user, hence forms a main lobe around that user, and hence effectively cancelling out the interference. This describes what I was talking about. So you realize that the lobes here are all equal. So a user can be found anywhere within this lobe, hence it doesn't efficiently cancel out the interference that much. In the adaptive array technique, however, you realize that it forms a main lobe around the user, hence effectively cancelling out the interference. This shows you that in the adaptive array, the desired signal is directly within it. So if you look at the interference, it's actually like away from the loop. It forms the loop directly around the user. With the switch beam technique, however, I realize the user could be anywhere within the loop because the loop doesn't adjust to the user, hence it doesn't really resolve its interference that well as compared to the adaptive array. This just shows the physical setup of the smart antenna system. For my project, I analyzed the smart antenna systems in a number of mediums. The first number of techniques. The first one is the carrier to interference ratio performance comparison. If you look at this diagram, for instance, you realize that with the mean 3 dB beam width, if you are comparing to the the mean value of carrier to interference ratio, it is observed that the switch beam technique actually performs better than the adaptive array technique, and this is because in the adaptive array technique, you have a high carrier to interference ratio with small beam width, but then you have a low carrier to interference ratio with high beam width. Hence, the mean value of the carrier to interference ratio is lesser than the switch beam technique. However, if you look at this graph here, we have it with the distance of the MS, the user, away from the 7 base station. You realize that though it decreases as the distance increases, the adaptive array technique actually performs better than the switch beam technique. Also, in this particular diagram, you realize that the adaptive array technique, though decreasing with increasing co-channel interference, still performs better than the switch beam technique in terms of mean value of carrier to interference ratio. I also analyzed the number of users that you can find in the cell or within the particular system, and you realize here that with increasing number of users, it's actually the adaptive array technique actually reduces gradually, and at the end becomes less than the switch beam technique when the MS is about 40. This is because with so many users in the system, forming adaptive loops around each user makes it very narrow, and hence it's likely to have overlapping, hence interference. Also analyze the uplink to downlink performance with multi-user detection performance analysis. It is realized here, if you look at the comparing the uplink GUS to the beam number of or antenna elements, realize that with increased beam number antenna elements, the GUS actually increases. But however, the adaptive array still performs better than the switch beam array, as you can see from the graph. Also, with increasing multi-user detection factor, it is observed that the GOS for the adaptive array is actually better than the switch beam. The same also applies for the downlink. Same also applies for the downlink performance comparison. I also analyze them in the ad hoc network, since this is quite different from the cellular systems. You realize that with increasing angular separation between say nodes A and B in degrees, the switch beam technique, it actually has higher BER than the beamforming technique, that's the adaptive array technique. Therefore, it is observed from this you can conclude, sufficiently conclude, that the adaptive array technique is a better smart antenna technique than the switch beam technique. This, in conclusion, I made this table to actually show the uh, advantages and disadvantages of the switch beam and adaptive array technique. In terms of integration, you can see that the switch beam is easy to deploy and it's of low cost. The adaptive array is, however, much more expensive and it has a lot of complexity in its transceiver. Also, there's less hardware redundancy. If you look at the range of coverage, there's more coverage in the switch beam technique as compared to the conventional systems, talking about the omnidirectional and sectorized system. But coverage cannot be compared to that of the adaptive array technique. The adaptive array technique actually has more coverage compared to all the other systems. Interference rejection is difficult distinguishing between the desired signal and the interference signal because of how the lobe is formed and the signal being within anywhere of the lobe. And does not react to movement of the interference. So, because the lobe is constant, when the user is moving from one place to another, it doesn't form the beam around it as that adaptive array does. In fact, the adaptive array focusing is not right. It focuses on the user and hence capable of nulling the interference signals and increasing capacity in that effect. Having concluded that the adaptive array is better than the switch beam array, I decided to go on to analyze the kind of algorithms that are used to further improve the performance of the adaptive array technique. I looked at the least mean square algorithm, the recursive least squares algorithm, and the constant modulus algorithm. These are just pictures to show you how the performance is. You realize with the constant modulus algorithm that there are a number of sub waves formed around the main lobes, hence it doesn't cancel out interference that's properly. With the least mean squares, you realize that though it does form its main lobes, there are still some narrow lobes that are formed around here that are many, and it makes it less effective. The recursive least mean squares, which forms like less nodes, less loops. This just goes on to describe what I was talking about. So you realize that least mean squares, you have less other nodes coming around here with the main loop, but then with the recursive, you have less of them, just about 2 of them here. You have 3 of them here. The CMA is noted not to have a very good main loop for carrier interference cancellation. I'll go on to the MATLAB to actually show you my program I designed for the. I focus on this project. I focus on the RLS and the LNS because they were able to form better loops, and I will show you the MATLAB program I wrote to actually show the error square, reduction according to the number of iterations. It will actually show you that the recursive least mean square performs far better than the least mean squares. Also, I went on to show the waveforms of the recursive mean squares and the least mean squares. You realize that with this being the signal and the signal and the input signal plus noise, considering the error, the adaptive desired output is much closer to the desired signal. However, with the same desired signal, you realize that the adaptive desired output is not close. It's a bit, sorry for that interruption. It's a bit it's not as the same as the you can obviously see from these two graphs that the recursive least squares is actually performing better than the least mean squares. To take you to my program. Okay, let's open this. Let me just delete for a short while. There we go. Okay, so I put in the number of samples. Let's say I put about 100 samples. The learning parameter, let's say 0.05, and the signal to noise ratio, let's say 50. There we go. So you realize here that with the error squares comparison, with RLS being the red light, you realize it forms and it degrades quickly over the number of iterations. However, the least mean squares still remains high for quite a period of time before it degrades. It shows that, like, the error in the error suppression in the least mean squares is not as effective as in the recursive least squares. I'll also show you the other codes that I wrote. Let's see, 2000, and let's see with one user. You realize from this the performance I was talking about. This is for the least mean squares. The final adaptive desired output is not as close to the desired signal, though it's it's less suppresses the noise introduced. If we, however, look at the recursive mean squares, recursive least squares, sorry, there we go, with the same parameters, you realize that this is the waveform formed. This is much closer to the main waveform. This is just to show you the code that I've written and to prove that the recursive least mean squares is actually a better technique to be used in the adaptive array technology than the least mean squares. This is my conclusion in this regard. The RLS provides better error correction capability than the LMS, as we've seen from the code. The rate convergence of the LMS is lower than the RLS, and the BER is higher in LMS. The beta error rate is higher in the least mean squares as in comparison. Though at the end, it is the only problem with RLS is more complicated than LMS. So it's a trade-off as to how much interference you want to consider, what the capacity demand is, and you could choose which to use. But in terms of better performance, RLS adaptive array technique is seen to be much more effective than the LMS adaptive array technique. Thank you. Hope you enjoyed the presentation.